Hello and welcome to the first session of the machining science course. So, before we start the course, let me give you a glimpse of what you should expect from the course and what we are going to cover throughout the sessions of the machining science course. So, in the introductory part of the machining, we will be discussing what is machining, what is the place of machining in manufacturing processes, how the various surfaces are obtained in machining, advantages, disadvantages, then the plastic deformation and the stress, strain, all those things we will be discussing in the introductory part. And we will also discuss the mechanism of plastic deformation in the atomic scale. Next, in the chip formation in machining, we will see the slip lines through which the deformation occurs and the chips are segregated from the workpiece. We will see the defects in the crystallographic structure of a material and how along the crystallographic structure or the plane or the slip line the deformation occurs. Elastic and plastic deformation in the atomic scale, the amount of shear stress necessary to affect the slip that we will discuss, and the basic machining processes followed by the cutting tools and the types of machining, orthogonal and the oblique cutting, just a glimpse what they are actually. Next we will discuss the types of chips, that we have the continuous chips, we have the discontinuous chips, and we have a type of continuous chips with the built-up edge formation. We will discuss the mechanism of the built-up edge formation, what is the physics behind it and how to prevent the formation of the built-up edge. Next we will discuss the tool nomenclature, that is how the tool angles are defined in different countries or different systems, for example, in coordinate system, in the orthogonal rake system, in the normal rake system and so on. Then we will see the how we can convert those angles, like suppose in India we are using the orthogonal rake system and we have a tool which is purchased from the coordinate system. So, how we can convert those angles and why we need to convert those angles. We will discuss the forces occurring during the cutting process and how those forces can be modeled through, we will discuss it through the Merchant's circle diagram, which you are very much aware of although. Now, from the Merchant circle diagram, after that we will be discussing the stress, strain, the strain rate, how to find them out analytically. Next to that we will be discussing the Lee and Schaeffer model, that is another model, but the principle is different than what the Merchants have used. We will discuss the nature of the sliding friction and how the friction in metal cutting happens. What is the difference between the friction in metal cutting and the friction, normal friction, sliding friction, and there will be a model which is called the Zorev's model that we will be discussing. We will discuss the turning process, physical parameters, forces, power consumption, material removal rate, time per pass and so on. Similarly, for the same thing we will be discussing for different other processes like shaping and planing, for drilling, for milling and so on. Then the forces in machining, that we will discuss how to measure those forces, what are the different kind of dynamometers that we have for turning, for drilling, for milling and so on. In the tool wear and tool life, we will be discussing the requirements of ideal tool material, for example, why the tool wears out, what kind of wear happens, and then what are the Taylor's tool life equation, and we will explain that what is the drawback of Taylor's tool life equation, how the Taylor's tool life equation can be modified and so on. After that we will be discussing the abrasive machining processes. There we will be discussing the nomenclature of grinding wheel, and then through a thermal model we will discuss how the grinding process can be improved by controlling different grinding parameters and how to control them. In the chip length in the grinding, that is the next topic in the grinding itself. So, we will find out analytically how the chip length can be found out in case of surface grinding, internal or external grinding and so on. We will discuss the oblique cutting, particularly in terms of the forces, in terms of the angles and how they are different when the tool is inclined with respect to the cutting velocity, as in case of the oblique cutting. We will next discuss the economics of machining. In the economics of machining, we will find out how to estimate the optimum cutting parameters at which we will get the minimum cost. So that the purpose of the machining is served, and it is not only to get the final product with the right kind of accuracy, shape, finish and so on, but with the minimum cost. And what are those machining parameters or optimum machining parameters for different criteria, for example, for maximum production rate or for minimum cost or for maximum profit criteria and so on. Next, we will look into the thermal aspects of machining, that is how to determine the temperature in the machining zone, particularly the chip tool interface temperature, and what different kind of models exist, and through those models we will be discussing the thermal aspects of machining. And finally, we will be discussing the surface finish, how the surface finish varies in case of the turning with a sharp tool, for example, or with a rounded off tool, for example, or in case of milling or in case of grinding and so on. Let us see the machining science. We will begin this course. Now, let us see that what is the place of machining in the GAMAC in the manufacturing processes. Before we start, let me say that the idea of all the manufacturing processes is to get a final product of right shape, size, accuracy, finish and of course, the cost. So, in that let us see how many engineering disciplines are involved. Let us say we have the ore here in the mother nature. Okay. So, this is the ore and this has to be found out, this has to be extracted. So, here we have the geologists, we have the geophysics people who are involved there. So, from this the core is extracted and this is being transported for the further processing. So, here the mining people are involved here. Okay. Mining people are involved here. Here the, as I said, the geology is involved here. So, after that this is being mined, the core is being ore is being mined and then it is transferred to the metallurgist people. Okay. Let us say this is a kind of a oven and here the metallurgist people will further process this, okay, and they will make the different kind of raw materials in the form of, let us say, this kind of a raw material, or it can be, for example, a round shape, okay, or it can be, for example, a shape like this, all right, and so on. So, it can be of course, a shape like this. So, this is the raw material which the metallurgy people will be getting from the molten metal which the mining people are supplying. So, here we have the metallurgy involved. So, this is the raw material that we are getting and this raw material will be processed. Okay. Now, this will be going into some sort of processes which are actually the manufacturing processes. Okay. So, here we have the raw material, we have the information, we have the energy involved there, and from the processes what you are getting is the final product. And along with that we are of course, we are getting the energy which is being converted to another form of energy, and we are getting the information. Okay. Along with that of course, we are getting the waste. For example, in case of machining, it is the in terms of the small chips which are being, which is a waste which is being removed from the basic workpiece surface. So, as we can see that there is a whole series or whole gammax of the engineering disciplines which are involved in getting the final product from the ore from the mother earth. Okay. And here let us see what is the position of the machining that we will be studying. So, here we have the raw material, as you can see at the extreme left. From the raw material we have the components, component 1, component 2 and so on. Now, all these components will be going through different kind of manufacturing processes. Okay. Now, these manufacturing processes can be either the constant volume manufacturing processes, as you know, or it can be material additive, for example, in case of welding, in case of additive manufacturing, or it can be a material removal manufacturing process, which is the machining. So, it can be either casting or primary forming, which are the constant volume. Here the volume is not changed, volume of the workpiece is equal to the volume of the final product, or it can go through the machining, or it can go to the secondary forming. Here all these are manufacturing processes, including the joining, finishing, assembly and so on. All right. So, here as you can see, the place of machining is here, meaning that all the components, the 1 to 6, all these components may not go through all the manufacturing processes. For example, here what is shown is the component 1 is going through casting, and after that it is going for joining. All right. Meaning that there are various casting processes which can make the final product, as you know that, or it can go through casting, then machining, and then it can go to joining and so on. So, for example, here the component 6 can go through primary forming and then directly to the assembly. Okay. So, then after that we will be getting the final product. So, here I wanted to show you the place of machining in the manufacturing processes. So, manufacturing processes are all of them: casting, primary forming, machining, joining, finishing, assembly and so on. All right. So, the next let us see how to define the machining, how we can say what is machining. So, machining we have seen that this is one of the manufacturing processes. So, machining can be defined as one of the manufacturing processes by which we can get the final product, okay, and that would be according to the shape, size, finish and accuracy by removing the excess material from the workpiece surface. Now, this removal of the excess material from the workpiece surface is contributed by a tool which we call as the cutting tool, and a contrivance or a machine which we call as the machine tool. Now, the different kind of shapes that we get during the machining, that means either a flat surface or a cylindrical surface or a tapered surface, or in machining, for example, other machining processes like drilling, we are getting a hole, we can get a tapered hole by, for example, by other processes, okay, and we can also get the slots, different kind of slots by turning or by milling, end milling, for example. So, these surfaces, different kind of surfaces that we obtain, it will depend on the different kind of relative movements between the tool and the workpiece. For example, if the workpiece is rotating and the tool is moving parallel to the workpiece axis, in that case you know that we will be getting a cylindrical surface. If the tool moves not parallel to the workpiece surface, but at an angle, so we will be getting a tapered surface. So, the tapered surface can be external tapered surface or it can be an internal tapered surface, for example. The flat surface we can get from the milling, okay, either it can be a slab milling or end milling as it is shown here, all right, or we can also get by turning. Let us say during the turning process, if the tool is fed perpendicular to the workpiece surface, we will get a flat surface which we call as a facing, okay, as you know that. So, here we can see the different kind of surfaces, these are obtained, and various surfaces are obtained as an interaction, as I said, between a workpiece and a cutting tool with the help of a contrivance which is a machine known as the machine tool. So, we have the tool, we have the cutting tool, we have the machine tool, and there is a relative movement between the tool and the workpiece to get the different kind of surfaces. Now, what are the advantages? Why the machining is so important and one of the most important manufacturing processes? It is basically because the variety of work materials can be machined. okay, which is difficult in case of let us say metal forming or casting, for example. As you know that if the form is shape of the final part is very complicated, in that case the pattern that we will be getting for making through the casting process, it is very difficult, and removal of the pattern is difficult, making the pattern is difficult, and so on. Most frequently used to cut metals is the machining. All right. Now, the second point is that variety of part shapes and special geometric features possible, such as for example, screw threads. Okay. Very precise screw threads is very difficult to get it through the metal forming or from the casting. Cold rolling is a process, but the again the accuracy will not be very high, not be as high as in case of machining, for example. We can get accurate round holes, which is very difficult through the casting or metal forming, as you know. Very straight edges and surfaces, which may not be possible in case of casting and metal forming, and that is why after casting and metal forming many of the parts go through the machining process to get these very straight edges and the surfaces that is possible to get through the machining process. Good dimensional accuracy and surface finish, which is very special characteristics of the machining, which may not be possible to get through the casting or through the metal forming. Generally perform, as I said already, after other manufacturing processes such as casting, forging and the bar drawing to get the surface finish, better surface finish, get the straight edges and so on. Only disadvantage probably for the machining process is that there is a lot of wastage in the material, meaning that machining by definition itself, it is the removal of excess material from the workpiece surface, okay, to get the shape, size, finish, accuracy, and therefore, that material which you are removing in terms of the small chips, that is actually considered to be a waste. So, therefore, wasteful of material and it is time consuming. Let us look at the mechanism of machining, how we can explain. Earlier in the very beginning, it was believed that when metal is cut, the material merely splits off in front of the tool. That is similar to the chopping of wood. Let us say, suppose we are chopping a wood, okay. This is a wooden piece and this is an X, all right. So, earlier it was believed that there is a crack formed and the crack is propagating, all right, and that is how the material is segregating in case of metal. Like in the case of the wood, they were thinking that there are the splits, it merely splits off, okay, in front of the tool, that is then X in case of the wood cutting, okay, and this is let us say wood. But in case of metal, it does not happen, that has been realized little later, and subsequently it was realized that the cutting of metal, this involves actually the deformation process. Further experiments revealed that the deformation was principally one of shear, that is a shear deformation, and that the type of chips varied with the work material and the cutting conditions. What kind of chips you will be getting, that depends on the work condition, that means the cutting parameters particularly, and that depends on the work material. For example, you know that if it is a cast iron work material, which is a brittle material, you will get the chips which is different from if you are machining the mild steel, for example, which is a ductile material. In case of ductile material, it is a continuous chips. In case of the brittle material like cast iron, for example, it will be discontinuous chips and so on. Extensive research revealed that the process essentially involves plastic deformation and fracture under high strain rate and the high temperature. So, this has been realized through hundreds of years that it is actually not the propagation of the crack like in case of wood chopping, but it is the deformation, and deformation is a plastic deformation. Okay. So, initially when the cutting tool starts interacting with the workpiece, there is a plastic deformation occurs, and because of the plastic deformation, the material gets segregated when it transforms from elastic to plastic deformation, and then it segregates from the workpiece surface in terms of the small chips. Now, since there is a plastic deformation involved in the metal cutting, so probably we should understand what is plastic deformation. particularly in terms of the metal machining, and there is the good example is the tensile test of a material through which we can understand the plastic deformation process. Let us say it is like this. We have let us say a mild steel workpiece, and the mild steel workpiece is being elongated, and the force and the elongation or the extension and the load are being measured. All right. So, if it is a mild steel workpiece, mind it is a ductile material. So, when we are applying the force, it is elongated up to a certain level, up to a certain point. Okay. And as we know that this point, at this point, the up to this point the material remains in the elastic stage, meaning that if we remove the load from this point, the material will come back to the initial position. Okay. So, from O to A, this deformation is known to be the elastic deformation. There is no permanent deformation happening in the metal. So, this point A, this is called the proportionality limit, meaning that here the load and the extension, it is proportional, load is proportional to the extension. All right. And once again, if the load is removed, it will come back to the initial position. Now, when it is crossing, the load is crossing from point A, it is going further. Now, the curve, as you can see, is no longer linear, meaning here the proportionality is disturbed, but the material from the point A to point B is still remaining elastic. All right. And then from the point B, the yielding starts, as you know, and therefore, the point B is called the elastic limit, meaning that up to that point B, it is elastic, and the elastic limit is crossed as it is crossing the point B when the yielding starts. And when the yielding starts, as you can see, that load drops, and there is a very small changes in the load, okay, with the proper extension from C to D, for example, and therefore, point C, this is called the lower yield point. So, this is the upper yield point and this is the lower yield point, meaning that here the yielding starts at B and this goes up to the C, and then from D it goes in a very non-linear way, and then as you know that here the strain hardening occurs. All right. So, from D to E the strain hardening occurs, and the point E is called the necking point. I am explaining later what is necking point, and then after the necking point is crossed, anywhere between E and F the material can get fractured. Material can get fractured, meaning that in terms of machining we can understand the chip is getting removed from the body of the workpiece. Now, let us see here the region OA, material exhibits elastic behavior, as I said, from O to A. Increase in length is proportional to the applied load, which is linear. All right. Now, from A to B, this linearity is lost. When applied load is removed, the bar returns to the original position. I already told that. Now, region AB, the material is still elastic. Relationship between load and extension no longer remains linear, but the material is elastic. Maximum load that can be applied without causing permanent deformation defines the elastic limit, that is the point B. This I already said. Beyond point B, metal no longer behaves elastically, and removal of the load leaves the bar with permanent extension, which is plastic in nature. So far what we said is there is an elastic deformation. So, from this point the elastic deformation is no longer there, it has become it will become plastic deformation, meaning that the deformation which is occurring in the material, it is permanent. If we remove the load, the material will not come back to the initial position, that is the point. Just above point B, okay, this is, as I said, called the upper yield point. Elastic behavior of the material ceases and yielding starts, this is called the yield point. Therefore, stress at point B is usually called the upper yield stress, and in the region CD, yielding in mild steel particularly is accompanied by a sudden drop of the load, as I said, and increase in length at approximately a constant load, here already almost constant load. Stress at point C is called the lower yield stress. This upper yield stress and lower yield stress is characteristic of mild steel, okay, caused by the presence of small amount of foreign metals in the material, like for example, it can be carbon, it can be nitrogen and so on. Most metals and alloys do not show this type of pronounced initial yielding, and change from elastic to elastic plastic or plastic deformation is gradual, but in case of mild steel, as we said, that this is the picture, all right. Now, region DE, as I said, this is the region of strain hardening. Following the transition from elastic to plastic behavior, the load required for further deformation increases, all right. Now, the material being able to withstand the increased load despite the uniform reduction in cross sectional area, this is called the strain hardening. This is the definition of the strain hardening, that is the material is the ability to of the material to withstand the increased load despite the uniform reduction in the cross sectional area. We will discuss the remaining things in the next session. Thank you very much.